more about it. Michael's been doing a lot of great work on bringing a lot of these ideas from machine learning over to us doing sciences, and so it's really exciting to have him here. So Michael, take it away.
All right.
Over there, and then that's on. No, it's on.
All right. Well, thanks, Nathan, and thanks to the organizers for having me here. It's nice to come and share some thoughts. So I've been thinking about these sort of, my background's actually in physics, and I moved into theoretical computer science and large-scale statistical data analysis. So I've been thinking about this sort of interface for a while, so it's nice to see things sort of maturing and the area sort of coalescing in some ways. So getting a chance to share some of those thoughts with you. So I'm usually not prone to overly immodest titles. But I felt like in this case, we have some nice results, and I think the title's justified, actually. That's not to say this is the final word, that's to say we sort of open the door, and now we can do stuff in terms of understanding what's going on, not just in terms of better job in computer vision and so on, but for a wide range of problems. And in particular for a lot of sort of scientific problems. So there's a request for volume. Is this,
This is on here, and I
for, who's this for? Is this for Intel?
So it's enough. This also goes up here. So let me see if they can volume control.
So is this any better? He's not nodding yet, so he probably doesn't. I can just shout if this is an issue, but yeah. Okay, so
magic happens. Okay, all right.
So there's a preamble, so I'll skip the preamble, and the tail end of the preamble was, I'm usually not prone to overly immodest titles, but in this case I think it's sort of justified, and I'll say why. And you should just realize, as probably a lot of you know, people that sort of have background in statistical mechanics sort of haven't historically been shy from sort of going and invading another area and claiming it for their own. So that's a little bit sort of what's going on here. So why does deep learning work? And so there's a lot of interest in understanding this, and people use stochastic optimization theory and VC theory. This is a theory of statistical learning. And you should just realize that physics and machine learning and statistical data analysis is a bit of a culture clash. And when there's a culture clash, sometimes you use a word in two very different ways. So theory, what is a theory? In science, theory means something. It means you go look at the world, you go posit something, you make a prediction, and the prediction's right or wrong. And if the prediction's right, that's good. Worse than being wrong is not even being wrong. This pejorative saying in physics, you're not even wrong. Meaning you make statements that are not falsifiable. So VC theory is not a theory in that sense. It's a bunch of theories. I mean, the theorems are good and they're useful for things, but it's not a theory. So using the word in a very different way. Stochastic optimization theory is not a theory, right? It says if you satisfy these sort of conditions that may be uncheckable, then you'll get some convergence rate patterns. So it's not a theory. So when I say why deep learning works, I want to ask a why question. So think of it as a scientific question. So in that sense, at a minimum, physics is informing the sort of form of the question I'm asking, and we want to answer a why question. And I'll tell you why deep learning works. Deep learning works because you typically train to good data, not bad data. That may make sense in practice, but if you're going to ask a scientific control, you should also train to bad data. We corrupt it in various ways. Deep learning works because when you train to good data, good images, good text, whatever, the training process itself engineers in correlations over many size scales. You see your eyebrows and your nose and your nose and your face and your face and your torso. Engineers in correlations over many size scales. And those correlations are well modeled by heavy-tailed random matrix theory. So think of what you might do if you want to model long-range correlations in fluid systems or in financial markets or something. So they're well modeled by heavy-tailed random matrix theory. And the heavy tails, the long-range correlations in the heavy-tailed random matrix theory, short-circuit all of the pathologies of Gaussian spin glasses. So Gaussians are easier to deal with analytically, but when they fail, you hit a hard wall. Spin glasses are sort of pathologically non-convex. And so it short-circuits all those pathological non-convexities. And you get a penalty surface that's sort of ruggedly convex, a little like when simulated annealing works as opposed to when simulated annealing fails, a low temperaturizing phase or something. So if, depending on your background, what I said makes a lot of sense, and you say, oh, I get it, that crystallizes a lot of stuff, and move on. Okay, so you can go home now, so you know what the next hour is about. If what I said didn't make sense, or half those words you didn't even know what they meant, then what I want to do is explain that to you. So you have a long paper And I got to know Charles some number of years ago, and we were talking at a meeting, one of these meetings, data science meetings in San Francisco. He said, "Well, this is a funny area. We know why deep learning works. It's because of dot, and where basically what I said, a slightly less mature version of what I said." And I looked at him, and I said, "Yeah, obviously." And I think he sort of looked at me like I was teasing him or something. And I said, "No, obviously. I mean, but the question's not, is that why it's working? The question is, how do you explain that to someone who looks at you and doesn't think, yeah, obviously." If someone who thinks about the world in terms of statistical learning theory, where you parameterize problems in terms of capacity and combinatorial VC type bounds and this sort of stuff, or someone who thinks about it in terms of stochastic optimization theory, and the 99% use case there is convex problems. And the properties here may just be qualitatively different, right? Because stochastic optimization theory predicts such and such. Go look at the world, it's exactly the opposite. VC theory predicts such and such. Go look at the world, exactly the opposite. So from that perspective, this is a great area because it's if we're doing physics-informed machine learning, it's like physics in 1920. You have this egregious experimental failings, and it begs for sort of a new theory of way to think about things. So physics-informed machine learning. So what is this? Some people say, I want to use machine learning to solve my physics problems. That's sort of like a minimalist version. So people say, I want to put physical insight into a model. And when Nathan first pinged me and said, it would be great to give a talk here, I was thinking about something related to this. Fortunately, you get a twofer. He also invited Ben Erickson, so Ben will be here. I think it's probably later today. He'll be talking about how we want to train a certain model. And it's not, why people click on ads, and it's not some, some image thing. Well, we really don't know the generative processes, and it just works for whatever reason. It's a physical system having to do with fluid flow, and we understand that the model should be stable. It should have stability properties. If you train the model, it's not stable. What if you force the model to be stable, to have the physical property, the physical symmetry that you get? And basically, it's a hello world version of I can predict the weather 5 days ahead instead of 2 days ahead. You cook stability into the model, you're robust for a longer time. And even that's a funny way to ask a question if you go to ICML, which is next week, or NIPS, which is in December. Because there they force the problem to be a classification problem, a static classification or regression or some sort of semi-supervised learning problem. They say, I assume the data comes from some distribution, and if there's a distribution mismatch, I get such and such. And that's not the way a physicist would think about the problem. A physicist, would say, I want to predict the world 5 days ahead, and I can't. And if I do something inside the model, I can predict it 5 days ahead, and otherwise it's 2 days ahead. So the distributions are mismatched. And you're doing a time series extrapolation, which is, time almost doesn't appear in the structure of machine learning theory, right? So you're making, the form of the statement you're making is very different. So you hear that later, and I'll talk about a slightly different use case for physics-informed machine learning. So the sentence I said earlier, deep learning works because the training process engineers in correlations analogous to multiple scales in fluid flow or protein folding. Those correlations are well modeled by heavy-tailed versions of random matrix theory. And those heavy-tailed short-circuit all the pathologies of Gaussian spin glasses. So you'll have ICML next week, you'll have a dozen or 2 dozen papers on Gaussian spin glasses. Empirical question, is that the way the data looks? There'll be 1,000 papers in ICML next week. One will ask that question. Maybe they don't have involved with this, but all the others won't. So ask a methodological question. So we're going to do in physics-informed machine learning here in that sense, and you'll get to hear a slightly different version of physics-informed machine learning later. All right. So with that background, I've done a lot of work on randomized numerical linear algebra. This is an area where you have big data matrices. Think of big Hamiltonians. What do you know about Hamiltonians? Either in the sense of a disordered system, like Wigner in the first place had to hypothesize random matrices, or whether eigenvectors are localized, right? Localized eigenvectors are important in the structure of randomized numerical linear algebra because we adopted a physics-informed perspective, and localized eigenvectors mean something in physical systems. You're a localized eigenvector. Right? Localized eigenvectors are part of this. This is not some condition number, some mathematical peculiarity. They mean something. So it's a localized eigenvector is important to that. So this has been, I've done a lot of work there, and roughly this splits the world up into low rank and not low rank. So what if you have correlations over multiple sizes? You're not cleanly low rank and not low rank. That breaks down, and that's not a problem with randomized numerical linear. That's just a problem with sort of linear algebra. It's hard to model things over many size scales. So if you're really honest about where this works and where this doesn't, you can look at the cracks or sort of where the proverbial bodies are buried and see, this is an interesting thing to push on. So we kept that in the back of our mind for all of some random matrixing, lots and lots of work. 99% of it is on Gaussian or Gaussian universality class. Is that the way the data looks? And if not, what can you do? Running involves a lot of things that work on foundations of data. Should the foundations of data touch data, or should it be a bunch of mathematical statements? So theoretical physics is a very practical business, as you know, especially if you're an experimental physicist, right? Theoretical physics is about computing numbers. If you're going to cheat, you cheat on mathematical niceties of delta functions, you cheat on sigma fields, and you compute a number. That's very different than the way theoretical computer science or mathematical statistics formulate problems. There's a lot of work in machine learning where the sort of mathematical rigor is the crutch, and the predictive quality in terms of how it might perform is not. So, which of the foundations of data be? Should it be more like theoretical computer science in terms of problems, or theoretical physics? So I make one claim, and some people might, want the opposite. So we're going to make methodological claims here, but we want to have a useful, we want a theory, and the theory is not a useful theory if it doesn't predict anything. So, practical theory for deep learning. You want to hand something to a practitioner and say, you're going to go to a desert island, you need a metric, so that tomorrow I'm going to give you a new neural network or whatever. You need to say whether this is good or bad. You need to say go or no go. And and we don't want to do this on MNIST, right, which is a toilet, and we want to do this on a real problem. Understanding why deep learning works. What does why mean? Are you going to ask a predictive question in the methodology of science? Are you going to ask sort of an a posteriori characterization like VC theory might provide? Something called the generalization gap. We'll get to this a little bit later. This has to do with large batches and small batches and something with some sort of interest. And sort of engineering better algorithms. So think of that as a very practical sense. So why does it work? Convex versus not. The taxonomy in terms of convex versus not is mathematically convenient. It's not something most scientists think about. Convex sort of means you're round and you can go between any 2 points in the body. And it's a very useful characterization theoretically. And so are these things convex or not? So we'll get that. Implicit versus explicit regularization. Sometimes you explicitly put regulation in, other times you just do stuff. And it has a regularization effect. So we'll get to that. Is deep better? I mean, how can shallow learning be better? I don't know what Ben's talking about, but maybe that'll be back. I don't know what he'll talk about. Why go deep? I mean, if shallow suffices, that's good. So deeper always sounds better, but is that the case? And can you understand when that? VC theory, which is a theory of learning. It's a way to predict generalization versus statistical mechanics theory of generalization. So, I could have given this talk 30 years ago, and there'd be people that would say, yes, statistical mechanics provides a theory of generalization, with generalization is related to volumes, entropies. And that was sort of vanished from machine learning in 1992 or whatever. And so now we're just saying, go and revisit old ideas. And so this is going to be sort of in the background, practical, very practical sense. So when do people stop training a state-of-the-art sort of neural network? Is it when some condition satisfied? Gradient zero, training error zero. The sort of dirty little secret is people just stop training when they get tired. There's a deadline tonight, I need to stop. There's something to push into production tomorrow, I need to stop. So, should I stop training? Or if I put a factor of 2 more after will I get a qualitative gain? That's a very practical question. No answer to that. Can we use labels or domain knowledge more efficiently? Right? People in machine learning parameterize this in terms of semi-supervised learning. But really, how does that enter into the structure of the model? Because these are much richer models than least squares and kernel least squares. Kernels have gotten a lot of attention in machine learning. Large batch or small design better and so on. So a range of very practical questions. So this started as beating up on Gaussian spin glass. Spin glass is a very hard thing. So if you shouldn't even mention the S word if you can avoid it in public. They're actually very hard, technically very complicated, very, very structured. And a lot of people sort of use it in a proverbial sense. It's like NP hardness completely. You just say it's something bad, right? And so there was a paper that was up, some of you, if you know the area, have probably seen this, and then a plot like this. So x-axis is something related to penalty, with energy in the statistics, physics lingo, but penalty in machine learning. Y-axis is some sort of count. You don't know about the details. And they saw that as you change something, you got a shape that looked like this. And they said, this is like a spin glass. And so spin glasses are very rich models. Do you need to go that far? And we saw that and we said, no, a random energy model, which is I'm not going to define what that model is, but it's a much more modest model that's used in statistical mechanics, gives you a plot that looks roughly like this. Now, of course, it's superficially different because you see I put the axes around, these letters are all backwards. This is a picture from protein folding back in the 90s. The x-axis is a free energy, and the y-axis is an entropy. And they didn't posit, spin glass models, they posited a much more modest random energy model. So you need this massive infrastructure of spin glasses, or you get away with something much more modest. And the reason that this paper didn't say yes or no to this was they didn't ask a scientific question. Right? They said, I see this, and I can justify, and then derive something. And so we said, do you need to do this, or can you get away with random energy, or can you get away with a correlated random energy? And how does that relate to the question I was asking before about these physical insights that might lie? So this got us thinking about this. So I want to talk about an energy. An energy is a physical thing. Physics, about energies. The way this interfaces to machine learning and optimization is roughly, it's the objective function you're operating with. It's a little bit more complicated than that, but roughly it's that. Now, a first-class citizen in statistical mechanics is free energy. It's the energy that's available to do work. And if you have a higher or lower temperature and other statistical mechanical ensemble constraints, but roughly it's the energy minus, say, temperature, which is a Lagrange parameter, times the entropy. So where does entropy arise in an optimization problem? You don't have a statistical mechanics ensemble, but it's known that stochastic optimization methods are good for a lot of things. And so they inject empirical variance. So think of that as a proxy for temperature. It's not a perfect match, but think of that as a little bit like that. So we're going to talk about an optimization function. In neural network land, it's going to be, a weight matrix, let me start on the inside, a weight matrix involved with something, it's some sort of nonlinearity. There's a couple of ways to put the nonlinearity, weight matrix, and you might have other spaghetti, convolutions and long-term layers and a lot of other stuff. So this is just think of this as a sort of caricature, but this is the structure of a lot of these models. Deep depends on how many iterations you have, but you can go wide and you can have lots of other sort of connections. And the MO in neural networks, which is related to what people in machine learning do more generally, but in particular neural networks, is to say, I want to train this on labeled data. I have data points, it could be images, it could be sentences, whatever, labels, plus minus one, I could have 10 classes, I could have 100 classes, whatever, using something called backprop. Backprop is an efficient way to propagate errors by minimizing loss. So I send it, the mental model you should have is, I have 10 layers, I send the data in, I make a prediction, I evaluate whether I'm right or wrong, and I backpropagate those errors. And when I backpropagate them, so I'm adjusting the weights. So I have weights, and I'm adjusting those weights. So that's going to be an important part of what we're doing here. And the energy landscape, the weights of W, the energy landscape is a part of the optimization problem parameterized by unknown elements of the weight matrices and bias factors, you can fold that into. And defined by the data. So what you do, you pass the data through multiple times and you run background. So in a sense, the energy landscape is changing, right? So imagine I have a quadratic well, it looks like this, and if I change the y is equal to alpha x squared, I change sort of how the Lipschitz curvature, how quickly it goes up. So I change, and that's related to an entropy, right? If it's down like here, I have a lot more states near the minimum than if my well looks like this. Okay, so the setup I wrote up before is not convex mathematically, right? It doesn't satisfy the property that convex bodies have, which is roughly, I can go from A to B easily inside the convex body. I can take the convex combination of 2 points inside the body, and all those points are inside the body. So it's not convex. And if it's not convex, a lot of theory, optimization theory and learning theory has problems, because if you're not convex, that's a much broader class of models than if you are convex. So what's expected is you look like this. Lots of local minima, lots of other problems. If you're convex, you have one minimum, or maybe something degenerate. So this is what you expect from the previous page, if you don't have a physical insight. Question, is this the way the world looks? Answer, empirical fact, this is what you see. These non-convexity problems are never a problem. Why? I don't know, that's a problem for theory to figure out, but it's just empirical fact, right? And it's been known for a long time. So you go back to 1991, and people that are leaders in the area now, were younger then, and they were saying, geez, we're training these neural networks. They were smaller then, we're training these neural networks, and we're going to get lots of local minima. So maybe the effective VC capacity is smaller because I count local minima or something like this. And then in 1995, they say, we just never have a problem with local minima. It's something else, we don't understand what it is, but we just never have a problem with local minima. And this is well enough known that by 2000, it's worked its way into textbooks. And local minima are just never a problem. Saddle points, there's other things going on, but you just don't have problems with local minima. So how can this be? This thing you set up that's nominally not convex. And a lot of theories guided to saying, how do you deal with these non-convexities? Empirically, it's never a problem. So what people do in the area is basically add more capacity. That just means make a model bigger and richer, and then regularize. So basically, you treat parameters in the model as a resource, like space, like time, like data, like any other sort of resource in computer science. Computer science is about managing those sort of resources. And then you cut back, and there's 10 control knobs to cut back. Physically, if you go to a lab and you measure something, you have a knob, and the knob controls a temperature. It doesn't really control a temperature. It controls something related, and you inject heat into the system, and it equilibrates. So think about what's your control knob here. So a control knob is you add a lot of parameters. That's easy to do. You add 10 more layers, you make the layers wider. How do you regularize? So you don't necessarily regularize in a traditional way, but if you do lots of other stuff, it has the effect of regularization. So what is regularization? So you can drop out. Drop out is sort of what you think. You drop something out instead of just drop. So that has the effect of regularization. It may control capacity. It may or may not be good algorithmically, but the early stopping. If I run 1,000,000 steps of a power method, I get optimized the Rayleigh quotient. If I run 10 steps, I might approximate the Rayleigh quotient insofar as the spectrum decays. Theorem, I exactly optimize the Rayleigh quotient plus lambda g. So these are nice clean functions. This is a hello world case, but two more general. Early stopping is known to have a regularization. You don't exactly optimize to today's data, you're a bit more robust to tomorrow's. Noise to data, you change back size in my stochastic optimization. I estimate my gradient using 10 data points or 100 data points. So 10 and 100, empirically that's a regularization parameter. People think of it as an endogenous computational parameter, but you change it, it has the effect of regularization. So the problem here is that everything's a regularization parameter. So people push stuff out. It's not like in science. Science has its sort of own problems, but it's not like, you could make code publicly available to competitors and exactly try and be as reproducible as possible. I mean, here's like an interpretive approximation of that. You push stuff out, there's a deadline, and the version of Python that you're using changes in 6 months. So literally, you can't even reproduce what you've done. So there's so many knobs and switches, and every one has a regularization effect. So if everything's regularization, you've emasculated the word of its meaning a little bit, right? So can we characterize a little bit more finely what's going on here? So we want to do this. And the other paper that informed our sort of approach, in addition to the one that I mentioned before about spin glasses, is this one. So this is something that ICLR is one of the conferences, one of the meetings in machine learning, sort of related to this topic. And this is not a paper that barely got in and no one's paid attention to. This was awarded the best paper, so the best paper by the community standards. And they observed that large neural networks can easily overtrain randomly labeled data. So I take a bunch of data sets, I randomize all the labels. Presumably that messes up all the structure and whatever. And I can run that process I was describing, and I get 0 error on the training data. Is that surprising? Is that not surprising? And popular ways to regularize, which basically means minimize f plus lambda g may or may not help. Meaning my traditional control parameter, which is I have an objective and I have a capacity term, which is a norm. This is ridge regular, ridge or last, so you put a g there. And then I cross-validate to get lambda. Popular ways to implement regularization may or may not help. And they had a sort of a catchy title, Understanding Deep Learning Requires Rethinking Generalization. And so a precursor to the work of all these other days, we said, rethinking generalization requires revisiting old ideas. Go read papers from 20 years ago. Admittedly, those papers are somewhat impenetrable, but statistical mechanical approaches and complex learning behavior. So what I'll talk about now, I already gave you the punchline, so you didn't go leave. Either you want to get the hour-long version of the punchline, or you figured you're here for the day, you want to sit through the rest, or whatever. So what I want to talk about is, this is the 20-page version of the punchline I just gave you, but admittedly, it's still a little impenetrable unless you love statistical mechanics. So what you want to do now is bridge that gap a little bit between what's obvious to someone with a physics sort of background and what's obvious to someone with machine learning who parameterizes things in terms of EC theory, and make it usable by a practitioner. You go to a desert island, here's a number to compute. So the ideas are here, but we had to couch a lot of the ideas in ways that are sort of more familiar to machine learning people. So, okay, basics of regularization, ridge regression. And there's a typo here, one of the W's is an X or something. So, AX equals B. This is just, and it's ill-posed, it's under, over-constrained, whatever, so I add a regularization parameter, and this is ridge regression. You could do truncated SVD. And you get F, some objective plus lambda, it's called alpha here G. So this is the same as lasso. Lasso is F plus lambda G. G is different, but this is the same as a regularized support vector machine. F, now depends on labels, plus lambda G. This is the same as lots and lots of things. F plus lambda G. All right, the lambda, it's an additive combination, and the lambda is a scale. Scale free, think of something physical, scale free. So it's a scale. Below that scale is one thing, above that scale is something else. If you know disordered systems theory, if you know fluid, dynamical systems, when you have scales separate, things are good, and when you have very divergent scales coupled together, things are interesting. And so, F plus lambda G. So it's often the rank of X, it's related to truncated SVD, which is the other way to impose that scale. And early stopping, truncated random walks, implicitly solve things like that. So 5 steps of a random walk theorem exactly optimizes F plus lambda G. Lambda depends on 5 steps. It can be 10 steps with a different lambda, but F and G are the same. All right, so how are we going to study regularization? So we want to adopt a scientific approach. So we're going to be physics informed, not in the way that, I'll give another plug to Stan will talk about, not in the way that we're going to cook that into the model, but in terms of the methodological approach. It's not just that we're going to use these techniques, we're going to adopt the following sort of experimental protocol. I'm a subroutine, you're the scientist. You want to know what I'm optimizing. I'm not going to tell you what I'm optimizing. Maybe I'm an adversary. I'm going to tell you a bad thing because I'll have a better market share next quarter if I like you, right? You're going to send me data. I'll send you an answer. Can you figure out what I'm optimizing? So let's work within the least squares. So I'm working with some variant of least squares. You send me a data point, I send you something back. If I always, and you want to know, am I optimizing least squares, ridge regularized, lasso regularized, this? And if I always send you back an answer that has a lot of zeros in it, you might say, geez, he's probably doing lasso because L1 gives you lots of zeros. And if I always give you back something that's spread out, you might say, oh, it's ridge because ridge spreads things out, right? And then you look inside my code, and we sign an NDA and look inside my, and it says, call CPX's lasso solver. Oh, you're right. Call LA Pack's ridge solver. Oh, you're right. Yeah. You look inside my code and it's some spaghetti mess. Because I was doing it before the deadline and there's for loops and go to loops. But I always return a sparse solution. If it walks like a duck and talks like a duck, right? It's very plausible to say I am implementing L1 regularization. I may not even know I'm doing that, right? But if I'm always giving you back that answer, that's what I'm doing. So we're going to adopt that approach. We're going to say, look at weight matrices of trained data sets and poke at them and see if we can understand the implicit regularization. And I think people don't know, and least squares is a toy case, but in these more realistic things. So we're going to do, to the extent possible, we'll turn off all regularization. So the idea is that different types of regularization are going to leave empirical signatures on W. W is the weight matrix, it is the model. There's some layers and stuff, but and so these different empirical signatures in the model. In the quadratic case, is it a tight well or is it a spread out one? We're going to the extent possible, because everything's a regularization now, turn off all regularization. So our goal is not to be 0.1% better on prediction, right? So we're going to turn off all regularization and we're going to turn it back on systematically. Because if my goal is better to be 0.1% better on prediction, if I change one thing, I have to change 10 other things to compensate to be 0.1% better on prediction, which makes it hard to ask the scientific question about why deep learning works, which is the goal of the learning. So we're going to change one thing, and we're going to sacrifice quality elsewhere by not optimizing that. So we're going to turn it all off. We're going to add it back on, and we're going to study empirical properties of W. And this is how model justified. All right. So lots of neural networks analyzed. It's hard to answer a broad claim by looking at one data point. So we looked at 100. I'll talk about just a few today. But we looked at over 100. The other thing I want to say is training is hard. A lot of people like to train neural networks. So we're doing training on one line of work. But training's hard. You'll actually hear a little bit about training later today in one context. But training's hard. So here I don't want to train, because training's hard. What I want to do is go out in the world and I want to measure, look at pre-trained models. This is a fact of the world, right? People say these models are best by some quality metric. I want to go look at them and say what makes them the best. So I don't want to do training, I want to look at, so I'm one or two places I'll train just to validate what we're doing, but I want to look at pre-trained models. An important sort of methodological contribution is don't train. Look at the world. Go measure something in the world and then try and sort of hypothesize. That's something that surprisingly is done very little. I think it's because Google and Amazon like to hire trainers because it fits into the pipeline. So we're going to ask this sort of scientific question. And so we want to do it on order 100 models. We're going to look at some older models, Lynette 5 and MNIST, which we pre-trained just for sanity check, and a couple small models for the time variation. But basically a wide range of state-of-the-art models, AlexNet, Inception, and 100 other things. And to a first order, everything's going to behave the way I described, and then there's some subtleties that are seen for second order. So what we're doing is going out, we're going to look at models, pre-trained models, people who pushed out the door and look at them. So we're running a statistical trial, like a drug test, and we go and ask the patients a year later, how did you perform in the drug test? We don't have access to the patients who died. So there's a selection effect here. No one publishes bad models. So you got to keep that in mind. So we're looking at the patients who survived. And we're going to poke at them and ask what their properties are. All right, so preliminary first results. So 3-layer MLP is a toy thing. Look at the entropy. So look at one layer, it's 3 layers, pull out one, or I'm looking at 2 different layers here with 2 different colors. Look at the entropy. So by entropy, I mean the entropy of the matrix entropy, which is basically the entropy eigenvalues. So the entropy goes down, and that looks like, I can come up with a statistical test, but if you're a physicist, you're going to say, that looks pretty reliable. I mean, you're going down pretty reliably, the curve's pretty smooth. I don't know what's going on there. We looked at that 5 times. That thing's like a real blip. And here it's going down also. So is the entropy decreasing? Here. So clearly the entropy is going down sort of. Of course, if your eyes are good, you know that it's going down from 0.91 to 0.90. So is it going down, is that really reliable? We saw that, clearly something's going on, but is it really that interesting? It doesn't matter. Right? You look at a stable rank. A stable rank is a soft version of the rank. It's a spectral to Frobenius norm ratio. It depends on sort of how spread out the aspect ratio is quadratic well, and sometimes we fix the volume of it. And that goes down. And for FC1 and FC2, that's the type of FC2, they both go down. So that's a real effect. These are very coarse measures, and I wasn't so excited about that. So then we said, look at scree plots. Scree plots tell you nothing, and here, look at this, they just go down to the right, so they really don't tell you much. If you actually look at the details, you can see it, but to first order, it doesn't tell you much, but we just figured we would include that in this. We're going to look at the scree plot, where it's actually hard to see slight differences. There are actually differences between those 2 colors and those 2 colors, but good luck seeing them, right? So you need to use the right lens, you need to use the right spectroscopy machine. So the same data on the previous slide I'm showing you here. Look at the empirical spectral density of the eigenvalues. It looks down. It's hard to tell some difference there, right? Look at the, you look at the singular values, and I'm not going to say why we're looking at one or the other. It depends on whether the matrix is square or not. But we're looking at through the right lens. What you see is one. So this is a histogram of the eigenvalues, an empirical spectral density. It's what motivated Wigner originally, right? Turn this thing on its side. You have a bunch of low-lying energy states, and you have some high things you're modeling as a continuum. So turn it on its side here. Red is initial. So why is, so if you're familiar with random matrix theory, when we saw this, we almost really wanted to fall off our chair, because it was clear what was going on, and it took a year to work out the details, but it was clear what was going on. So boom, so we see this. This is a quarter circle plot. It's like Wigner semicircle, if you're familiar with that. So red is Wigner semicircle. Does that say something deep about why deep learning works? Or red is the initial state when I start training? Or does this say that the right place? The what?
Because you started at the right place.
What this says is that people train by initializing randomly. So that's all this says. So this is a sanity check, but it doesn't say a lot. Okay, so after training, now we get 99.8 or whatever the percentage we need to get is. This is what it looks like in blue. Boom, 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 boom. A statistician will look at this and say, oh wow, that's amazing. That's a spiked covariance model. Random plus 5 eigenvectors that stick out of the ball. Spiked covariance model. We saw that, so the reason the entropy decreases is because these things pull out just a little bit. This is who knows what's going on. These things pull out just a little bit. That's the ball game. Which is why Actually, it wasn't cheating when I ignored all that lower scale, right? So that's the ballgame that we've done really well. All right. Training's hard. Computing eigenvalues is easy. We can do it in 5 lines and 5 lines. So this is literally what we're doing, right? All right. So how does this behave as a function? So one control knob is the number of iterations. How does it behave as a function? The number of iterations, how do you see the data? Here's we start at random, after 40, passes over the data, boom, blip. You're at 3. If you do an order of magnitude more, you get up to 4. So you train and train and train and train, you get a marginally better. Now, this is an ESP, an empirical spectral distribution. Does this say anything about, did I just pull some statistic out of the air? What did I just do? So what we're doing here is looking at this or functions of this provide a posteriori quality metrics of regularization, right? So the stable rank, if you want to say it's a robust version of low rank, is basically the spectral supervenience one. If you fix the volume of this, it's the ratio, it's the magnitude of this largest component. You know, so if you don't fix the volume, it's the ratio of the 2. If there's a gap here, see there's a bit of a gap right there. That's a good thing. It's like a spectral gap in linear algebra. It's a notion of robustness. It's an a posteriori metric of model stability that says there's a scale, and above that you behave this way, and below that you're noise and you can ignore it. Question?
It might be there's an eigenvalue within the random range, which is not nonsense. It's the right thing, it's just small.
So there might be an eigenvalue within the random range that's not nonsense. It may just be sort of small, and so I'll say something I was going to get to a little bit. So the following is true for M, it's not the 3-layer MLP, but cut off right there. Keep out of 500 eigenvalues, keep 8. On MNIST, if I do that, I can get 90, and now I try and optimize as well as I can. If I'm on MNIST, I get 95% prediction quality. So 95% good or bad on MNIST.
It's not very impressive.
So it's not very impressive, but that's because your reference state is 99.8.
Yeah.
I think it's not bad. My reference state is 10. There's 10 digits, randomly flip a coin, you have 10. So to get from 10% to 95, I need those 8 eigenvectors out there. To get from 95 to 99.8, I need to get that bulk. So there is information in that bulk. There's a lot of information. It's hidden from the lens. I'm using a telescope or microscope, right? There's information there. It's to first order hidden with the telescope I'm using. So you could ask more refined things about what's going on and try to be axis aligned in the bulk. And we have some results there, but that's hidden from the lens of global eigenvectors. But there certainly is information there, yeah. And then another question is, what's going on at the edge? We'll get to that. That's one of the important things. What's going on at the edge.
What model was that?
This is a 3-layer MLP. The answer I gave was for MNIST, and I have it a few slides ahead, but since the question came up, the answer that I answered was for Lynette 5 model with MNIST.
So these are the characteristics of the matrices, the weight matrices, right?
Yeah.
If you have a pipeline, you try to explain why the pipeline works in certain way, by the property of the matrices.
A pipeline means 10 layers on.
Sure, but you're ignoring the non-linear that connects them.
Yeah. So this thing, this is a time, I'm not having a chance to go through all these, but a general rule is you see something like the following. This is FC1 and FC2. There's 2 different layers. They both go down. The later ones you tend to see this more prominently. We're going to apply this mostly to vision problems. There's a lot of convolutional stuff going on. What you would expect would make the theory less relevant because you're squeezing out local correlation. So what we do, you can apply this to convolutional layers. You see what I'm talking about, but it's a messier version of it because when you matricize those layers, you damage the sort of structure. So for most of it, I'll show you pull out fully connected layers towards the end, in the middle, beginning, or wherever they are. And you see something like, if you're later on, the results sometimes are more prominent. But there's a lot of other stuff going on. Time permitting, at the end, I'll mention, you could say, can I look at 10 different layers and can I come up with a measure that's an average of those layers in some way? And the answer is yes, because some subtleties there also. So yeah. All right. So when we saw this quarter circle, we said, wow, this is fabulous. So now you got to spend a year working on the details. So here's the 101 and 102 and 103 on random matrix theory. So the 101 is that if you have a random matrix, you get this thing. So you saw the quarter circle version, the semicircle. This is the Wigner semicircle law. And there's 2 things about this. One is, and it doesn't take forever to get to the asymptotic regime. You can get to it pretty quickly. You get a deterministic function, which is the semicircle. And you saw the quarter circle version of that. And there's interesting, so that's a bulk, and there's interesting stuff going on at the edge. And the edge doesn't behave in a Gaussian way, it behaves with what's called Tracy-Whittem fluctuations. I gave a talk at Davis, I think it was earlier this week, and Tracy was there and said, how do you know that certain properties you're seeing are not fluctuational effects, which is, of course, exactly the question you want from Tracy, because there's a large right deviation, and so we get that, they're not. So problems with the Wigner, the weight matrix is usually on square. You typically do a single run. I'll show you averages of many, but if you were to go to the desert island, you only have a single run, so how do you use this? That's the 101. So what we're interested in is bulk statistics and local edge fluctuation. So we're going to construct a theory based on that. 102 is Marchenko-Pasteur, a bunch of equations. The same ideas go through. So you don't get a nice semicircle, you get some other functional form that depends on the aspect ratio and variance parameters. You get a nice deterministic functional form, and you still have the same Tracy-Whittem type fluctuations at the edge. So there's a bulk, there's an edge. And we want you to understand those properties in order to make a prediction as to what's going on. 103, this is where it gets interesting. The heavy-tailed version. So basic Marchenko-Pasteur. If you have Gaussian entries or anything roughly Gaussian, you get a Marchenko-Pasteur distribution, you have Tracy-Whittem fluctuations. There's no far tail. Spiked covariance, bulk, plus a few eigenvectors. It's a perturbative approximation of bulk. The same sort of ideas go through. Heavy tails is a much harder thing to deal with. You don't get moments concentrating, a whole different size scales. So the situation is a little bit more complicated than I'll describe, but think of it as a power law. You could model levy flights, but think of it as what I'll talk about here is a power law. There's a power law parameter. Think of it as three regimes. One is your heavy-tailed in the 0 to 2 regime, very, very sort of heavy-tailed, mediumly heavy-tailed 2 to 4, and moderately heavy-tailed greater than 4. So here, 4-moment things, 4-moment results would hold. Here you're so heavy-tailed that if you exogenously specify properties of the matrix entries, you see them in the eigenvalues and you're dominated, it's extreme values, you're dominated by the largest entries. You actually have other universals. So each of these is a universality class in the same way that things that look Gaussian are in the Gaussian universality class. Here you have three qualitatively different universality classes. You actually have one when mu equals 2 and mu equals 4, but we don't expect to resolve that empirically. So if your mu is very large, you have heavy tail local edge statistics, but you're not. It can be hard to resolve the difference from a poor fit to large mu, very weakly heavy tail. It's sort of the same as a poor fit to a Gaussian. It can be hard to tell the difference. If you're extremely heavy-tailed, you're dominated by individual matrix entries, so you can sometimes resolve it. Here, if you're heavy-tailed in the model, you'll be heavy-tailed on the empirical spectral distributions. You wouldn't have to expect an edge, and the power statistics will be for shade. The interesting regime is this intermediate regime. We're going to couple the scales together in a much stronger way. Here, asymptotically, so if I'm a theorem proving one asymptotics, I get one set of results. Finite n, I get a different set of results. So the finite n corrections are non-asymptotic perturbations on the asymptotic state, which makes life harder. So a lot of open, sort of interesting theoretical questions. People want to look at a log-log plot. That works if your exponent is 1, extremely heavy-tailed. It sort of doesn't work otherwise, so you got to be very careful. A lot of finite size effects. So we stole a couple pages. We're using random matrix theory, but not being pedantic about the formal statement of the axiomatics, we're using it. So the results that we found most fruitful here were Bouchard and Potter sort of results. They did statistical physics applied to finance. And finance is, is an area you can become a billionaire if you're right 51% of the time, right? You just need control on the downside risk. And so they really ask different questions than you'd ask in machine learning. They would say, I have a parameterized model, I'm going to model the finite size fluctuations and want to understand the finite size effects. And these matrices are 500 by 1,000. So large enough that if they were Gaussian, Wigner kicks in, Marchenko-Pasteur kicks in, but nowhere near large enough that the asymptotic regime kicks in if you're heavy-tailed. And so the finite size effects really do dominate here. All right, more detailed empirical results. We looked at lots of things. Linnet is a state-of-the-art model from 20 years ago. The reason that's not why you hear about deep learning these days. You hear about deep learning these days with balance and a bunch of things since then in 2012 and 2013. And so everything since then is going to behave. So Linnet's going to behave in one way. Everything since 2013 behaves in a qualitatively different way. So a bunch of tabular numbers to illustrate what I'll describe now. Look at Linnet 5, FC1, the fully connected layer 1. You see similar things for the other things. This is the empirical spectral distribution. Boom, 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 boom. red is the best MP fit we could find. We did it by hand. We don't have a way to automate it yet. So the best, and I mean, come on, that is pretty good, right? There's a fluctuational effect here. Tracy Whittam sort of fluctuate. I don't know if that's inside the bulk or not. What I do know is that and 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 that, which I'm showing here, are not inside the bulk. So this is real signal, well outside the bulk. I can show you 100 other plots. In the interest of time, I won't. I'll show you one. And then I'll show you an exception. But everything since 2013 looks this way. And this is actually very different. So this is FC1 and FC3, two different layers. What you see here, the edge effects here, you get a little blip that sort of points down. The edge effects here, you get a much stronger bleeding up. This sort of points upward. If you see FC3, which gets to where you are in the hierarchy, really you've eaten out mass from the random structures. You're qualitatively different than a random basal level. You have a lot of mass here, and you bleed out. And I don't stop before I go out to 20 here. I just zoomed in here to see that. You get a lot of extra mass here. So this really has a heavy-tailed structure. So here I'm showing you a linear scale. If I show you log linear, log, I mean, I can justify this thing. But this heavy-tailed doesn't just mean I have stuff out there. It means I'm moderately well to very well approximated by a power law, say. So it just doesn't. I'm not using the term semi-formally. It's as formal sort of as you would as a practitioner if you want to use the term. But I can show you 100 other things that look like this. Sometimes it's interesting to find sort of exceptions that prove the rule. Here's one. Here's inception, where you see something that is not at all well described by heavy-tailed, small eigenvalues. The interesting thing is here you have a dip. Almost goes to 0 limit. So this looks, so I haven't, whenever I've seen a dip like this in real data, it's because you took two models, you pasted them together, and you didn't optimize something out. So I don't know the background on inception or not. I've given the talk a number of times and thrown this out, and no one's come up to me afterwards and told me. But if anyone knows the background of inception, I'm sure it's because they pasted two things together and didn't optimize this enough. And so, so that's sort of interesting because I'm guessing that would suggest that you could take this model, you could optimize it more, flatten out, and get more heavy tail along the lines that we're talking about. Okay, so here's a theory. So we looked at a bunch of, understand what we did so far. We looked at the world. We didn't train, except in some cases. What we've seen is that all of the stuff, the net 5, stuff from 20 years ago looks like this, boom, 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 and everything else since 2013 looks like this. Heavy tail. Question?
So I just wanted to ask a question. So if I understand right, there's another possibility for how you could get what you call heavy tails in the eigenvalue distributions. Can you hear me?
Yeah, barely.
Okay, so I'll try to talk about it. There's another possibility for how you could get what you call heavy tails. So the possibilities you listed were that the random variables in the matrices were themselves drawn from heavy tail distribution. But another possibility is that there are correlations that are being built in between the variables, which also will do this. And it's a different mechanism, one that I think is quite plausible here, if I understand it correctly.
So,
you're training.
yeah.
And so I guess I was wondering, before you go on to the next topic,
The next topic is that. So the question is, one way to get heavy tails is to sort of model it and exogenously put on heavy tails. I haven't said anything about mechanisms except my very first sentence, but a different way is to have, there's 10 mechanisms in statistical mechanics. There's self-organized criticality, there's sand piles, there's a lot of ways. What's the mechanism here? And in particular, it's plausible that there's correlations going on here. So deep learning, why does deep learning work? Because the training process engineers in correlations over many size scales, and those correlations over many size scales are well modeled by heavy-tailed random matrix theory. And though the heavy tails there short circuit the pathologies of Gaussian spin classes, and that's why you get a rugged convexity. So you're exactly right. So the reason this works is because the training process engineers in correlations over many size scales. We're using random matrix theory as a model for signal, not as a model for noise, as a model for signal. So that's exactly right.
But if there are correlations between the variables, though, this Martinez sort of trick of pulling out outliers is very dangerous because Martinez sort of assumes that.
Give me complaint in 10 minutes if I don't satisfy you. You're totally right, and well, the leading order bit is a different subtitle I could have had is traditional and heavy-tailed self-regularization. Traditional self-regularization is ridge. It's exactly what you're saying. There's a scale, peel those off, that's noise. That totally fails on everything since 2013 for exactly the reason you're saying. It's because what's really going on here is you have a heavy-tailed regularization. You have a regularization over many size scales that's not a perturbative approximation of any of those cases, and it's exactly the sort of thing you're alluding to. Yeah. which is interesting because it cuts across exactly the way a lot of machine learning, I mean, aside from generals, it cuts across exactly the way machine learning people parameterize problems. So this is, in a sense, the physics-informed aspect of it. I mean, modeling those correlations over many size scales is a very natural thing physically, but it's a very unnatural thing in terms of the limit state that algorithm, theory of algorithm parameterization goes to. All right, let's see. All right, okay, so we've looked at the world. We've measured a bunch of things. So here's a theory. So the theory is going to be about limit states of learning. Remember, we're looking at ESDs, and this provides an a posteriori characterization of regularization, so possible end states of modeling. One end state is essentially random. There might be signal here, but the signal's sufficiently fine that I can't see it with a global eigenvalue lens. So I could get an ESD that looks roughly random, where the signal's buried in there. You know, statistically, it's going to be hard to find the signal inside that bulk unless you make additional assumptions that their axis aligns or whatever. You could bleed out a bit of mass, in which case you might be in the fluctuational regime, you might be pulling a signal out. I mean, bulk plus spikes that stick out. Bulk decay, you start to eat out the bulk, you start to eat this out a little bit. You have some spikes, but you also eat this out and you have mass here, which is well coupled with the bulk. And take it a bit more, the Heavytailed case, where you're not even a perturbative approximation of any of those. And you can get a corner case where your rank collapses also. Here's a slide that sort of says slightly more formally how to do all that. But the idea is this slide just has a lot of information about look at bulk statistics, look at edge statistics, be overly careful and pedantic about exactly these issues. Where are you at the bulk? Are you pulling stuff out that's fair to pull out and so on? Lots of technical issues. Okay, smaller, older models can be described perturbatively by Gaussian random matrix theory. Look at Linnet 5, it's bulk, it's spikes. It's ridge regression with bells and whistles, right? So you don't exogenally force this, the training process gets this. And you can imagine that if I have some rank 5 approximation, and if I run SGD, you can imagine that the end of the training process could be bulk plus spike. I'm sure you could prove it here at that point. So older things look like that, and that's sort of nice. It's a way to characterize in a much stronger way the implicit regularization result I described before about 3 steps or 10 steps of the power method. And this is true for everything prior to 2012. So this is a nice result. And a lot of the heavy-tailed stuff I'm talking about here is of interest for images, text, and maybe state-of-the-art. This is the design principle. Why are you going to follow machine learners say and optimize to death what they say the best thing for SGD is if that's been optimized through the lens of computer vision? I mean, if this is a design principle to say maybe I have a physical system, I want to encourage it to be a perturbative approximation of something. And in a lot of physical systems, you have to see exactly that. In other words, you may not, in which case the design principle won't afford that matter. So, this is lambda, f plus lambda g, you cut there and above that signal, below that's noise. There may be signal buried in the noise, but as a modeling thing. All right, what we think is going on more generally is the following. W, the weight matrix, is strongly correlated. You trained this thing to death, you engineered in correlation between your eyes and your nose and all these other things. What we're doing is modeling these strongly correlated systems in the sense of disordered system theory, say. Soft condensed matter is sort of the way we think about it. In this case, the ESDs will have heavy tails. There's lots of details there. So we're making a universality class statement. The ESDs don't exhibit that universality. And so in particular, in a lot of cases, we can put the extreme ends of the ESDs and still have these properties. So we don't have a way to sort of automate this yet because the most interesting universal regime is that intermediate regime, and the finite size effects dominate. It's a little more complicated than I'm alluding to. But we're using known results from random matrix theory, in particular polymer theory. So the way random matrix theory is used in polymer theory is very different than the way it's used in solid-state condensed matter physics or quantum field theory, where you really go to a certain limit. In polymer theory, it's a very different limit. So protein is not a random walk. It's not a self-avoiding random walk, although it's a marginally better model way to model it. It's a self-avoiding random walk where you have correlations built in every 3.4 amino acids, because that gives you an alpha helix, and every 10 or 20 amino acids, because that gives you a beta sheet. So you have, and then you have tertiary structure. So you have very subtle correlations built in, sort of analogous to what's going on here in the training process. Larger models, everything since 2013, exhibit this novel form of heavy-tailed self-regularization. So what's the mechanism? I don't know, I could throw out a bunch of ones, we just talked about a couple, but this is an a posteriori characterization of regularization that's going on. Somewhere we suspect. So there's no single scale threshold. I can't cut here, signal, noise. No simple low rank approximation, correlations from contribution of all size scales, and really cannot be treated perturbatively. And I can talk offline about the second order bits. The first order bits is that everything since 2013 behaves this way. You can look at eigenvalues, lots of other things, and you see some of the sort of results. So varying batch sizes. So how would you use this? So we want to make a prediction. We have a theory. A prediction is that, we just posited something exists. Does this? Can we find all 5 phases, or is this just something I just drew with MATLAB or Python or whatever is my highlight, right? And so the scientific matter would be to predict that something exists by changing one parameter, not a dozen. So we want to do, and we can do it with a bunch of different parameters, but I'm going to talk about batch size because there's some interest in that. So theory should make predictions, do these phases exist as many, many knobs. So what we want to do here is tune one knob, and we're going to look at batch size. I'm running a stochastic gradient descent algorithm, push data through, back proper errors. How large is the batch size that I use to estimate the gradient? That's what I mean by batch size. And we want to show that a small model with mini version of Algebra, we can apply this to something obscenely large if you gave me $1 million in GPU average, but right here it's for smaller trainable models. Large batch sizes, we'll see empirical factors. It's known that large batch sizes, you tend to get worse generalization accuracy. I can train today's data and see as people like, and machine learning people like large batch sizes because for latency and throughput reasons. So you can compute stuff fast. Of course, the thing you compute fast is oftentimes worse in the sense that there's worse generalization accuracy. So the generalization gap, with all else being equal, small batch sizes lead to worse generalization results, more implicitly self-regularized models. So can we see that in what we're doing? And in particular, can we exhibit all 5 phases? And so the answer is yes. And so by varying batch size, as a stable rank, an empty soft rank, there's a different notion of stability or robustness. Both get more regularized when you go to smaller batches. And the accuracy down is good, so this is the part of the scale. See, down is good, and large is to the left. So let's keep you on your toes. But if you parse that, you get better as you get to smaller and smaller batches. Question, why do you have such a big training test gap? Why don't you drive that to 0? Answer, because I want to vary one knob. I want to ask a scientific question with control. I can drive that to 0 by fiddling with other knobs, but I want to vary just one knob, so that's why we see a big gap there. We chose the optimal value for 512 or 1024 and then decreased it. So optimize at 512, increase batch, 1024, 2048, decrease it down, 64, 32. How bold are you? Keep going lower, 32, 16. So we kept going. Increasing batch sizes lead to better results and induces strong correlation to W. Increasing batch sizes lead to worse results. It washes out correlations in W. And so what you see is batch size 500, you're random, 250, batch size 100, get a little bit of a blip here. We optimized here, the only thing we're changing is batch size. 32, bold plus spike on 32. Are you bold enough to go to 16? 16, put spike, lead mass up, but you haven't eaten that away. 8, maybe you're eating that away, I don't know, but if you push it to 4, you're eating that mass up. Go down to 2, here you're heavy-tailed. So you exhibit all 5 phases just by changing batch size. Decreasing batch size induces, so here's a plausible sort of mechanism. If my batch size is smaller, it's easy to squeeze out fine-grained correlations. If my batch size is larger, I can't. Someone might say, geez, if I just train forever, I'll be able to squeeze that out eventually. And the answer is no. I mean, if you view this thing through the lens of statistical mechanics, there's other effects going on, and you might hit a wall in terms of a phase transition. And so I don't want to say you always get small is always better, etc. I mean, here's an example of it. If you had large, if you had this, you had that, you could probably have much richer phenomena.
So are you looking at the final train weights?
This is the final, take, train this optimally to 99 point whatever, and vary just batch size. Yeah.
And so that's okay.
And then train, but don't touch any other control parameters, only that. And train at that batch to plateau.
And the function values are similar across the experiments?
Function value, the quality changes. So my prediction accuracy goes from at whatever.
Oh.
So the quality changes.
So you're training
at different batch sizes. but don't vary with any of the other control norms.
But the training loss also changes between those.
The training loss also changes.
Okay.
So at least as importantly as saying what you change is saying what you don't change. And so, you know, there's a lot of things that aren't changing here, you know, and we're training, you know, a fixed number of epochs, you know, et cetera. So, and we've seen if you use an epoch budget versus a wall clock time budget, I mean, it's a rather complicated space. So what we're doing here is showing that we can exhibit all 5 phases by changing 1.5, yeah.
Like which has the lowest training loss of those 6 figures in the next slide?
Training,
On the next.
what is the lowest training loss?
Which does the best? Like,
We can drive the training loss down. I mean, so blue is training. Small backside gets, you know,
adds the back is okay.
did I mess up 1 or 0? Oh yeah, accuracy is 1, so loss is 0 or something. This is accuracy, not loss. There's a slight difference between them. So, yeah. All right, so in the interest of time, so how do you apply the theory? So there's a question, you know, you have 10 layers. What we're computing for each one is a power law exponent. Why don't you take the average of them? The average of them is with very small power law exponents related to a Frobenius norm, if you relate it the right way. So if you take the average, as go to the desert island, compute the average of your power law fits, that's good but not great. If you do a weighted average and you justify the weights by an appeal to universality in that middle regime, the right way to a weight is based on the spectrum norm. So I average weight matrices by their size. Their size is measured by spectral norm. For very low power law exponents, that corresponds to a Frobenius norm. People have looked at products of Frobenius norms as a way to regularize, and in log scale, that's a sum, so it's an average. This is different than the Frobenius norm. We can exhibit examples where this metric and that behave the same way, and the reason the product norm is 30 people like that, and they've applied to very small things. This is state of the art. You can take this metric, apply to state of the art. If you look at compressed or distilled models, so Intel wants to compress models, you know, remove layers with distillation or compressing, you know, a small number of bits, you tend to mess all this stuff up. With a little bit of retraining, you can pull this back out. In a bunch of cases, because of the way they implement that, the Frobenius norms get worse, which suggests that the models are going to perform worse. They in fact perform better, and the weighted power law metric, you know, performs better. So let me conclude with just a picture as to why this works. So the picture is going to be the following. So the training process, if I start off with something random, you know, it's well modeled by a Gaussian random matrix, and it's known that if you go to the low temperature phase there, you're going to the spin glass phase, and you're pathologically non-convex. If you engineer in correlations over many size scales, which plausibly the training is doing, and the page we stole from, you know, polymer theory, think of protein. Natural proteins are very different than random heteropolymers. A natural protein, if you heat it up and cool it down, you always get the same end state. Random heteropolymers, that's not. You can heat up and cool it down to the age of the universe, you'll never get the same state, right? Because you're in the pathologically non-convex state. And the reason is that you're engineering correlations over many size scales in a protein. So this has been modeled with heavy-tailed random matrix theory back when statistical mechanics of neural networks was being done back in the 90s. We're saying now, steal a page from there, and if you engineer in correlations, whether it's in proteins or the weight layers, you're going to get heavy-tailed random matrices, and what that does is short-circuit the non-convexity. So a way to quantify that is to look at, you know, the number of minima near the ground state in entropy scale. So in a very idealized case, there's own Bouchard, so to show that heavy-tailed random matrices, you don't get minimum concentrated in the ground state. So the claim, based on what we're saying, is that that's going to be true more generally in the universality sense. We're modeling real signal with heavy-tailed random matrices, and so we're claiming that you're going to get a rugged convexity for that reason. And so the reason these things work is that, you know, of course you find the minimum. You know, you have a stochastic optimization with a lot of variance. You never see that bump for that reason. You get something here, and all the effort is to get something marginally better here. That's why people are spending all the CPU time optimizing that. So with that, let me wrap up, and I'm going to be around for today and tomorrow. So come and tell me it's wonderful, it's terrible, and we can wrestle about it if you want, or we can argue about it. So thanks for your attention.
Open the floor to questions.
So, so what about the quality of data that you use to train? Is this a different node that also has sort of the same condition between the phases?
The conjecture is that, the question is, what about the quality of data? If you randomize labels, you mess this stuff up, which may be plausible, but the question is why? With RBMs, there was a certain ideal case. There's a very clean mapping to statistical mechanics system, and why there's a lot of interest in this. But the claim would be, a million other things boiled down to something like that, even if you don't have quite as clean a mapping. And this is 80s, 90s, maybe 70s. I mean, Cowan did stuff in the 50s or 60s. So the claim would be that any of a wide range of systems, any non-trivial system, viewed at through the lens of statistical mechanics, which is roughly let model quality and number of data points diverge together. You need to have a typicalness assumption. So, if you do that, then there's sort of two things that matter. It's like a pressure, a temperature, and an canonical, or whatever else. There's a load parameter, and load was a way that they would characterize something having to do with the quality or quantity of data. So in a very special setup, it meant one particular thing. But here it's something related to the quality or quantity of data, and then there's temperature parameter. And most of the knobs are talking about batch size, the learning rate, which is step size, drop. These are ways to instantiate something correlated with temperature. I don't know how to define it exactly because I'm not in a clean ensemble, so you have to define it operationally. And what you're talking about would be something like a load parameter, and you'll get some phase space, analogous to what people saw before. So if you change the quality of the data, if you mess up all the labels, there may still be structure in the unlabeled part. If you mess up both, everything should get bad. And we see that. And so, for example, the heavy-tailed structure, you would expect that you're not going to, you introduce a scale, you're not scale-free. And so what I'm saying you should damage, and you very quickly damage it. So I think the way to think about labels is it's something like a load parameter. And so you can, load is on the x-axis, temperature is on the y, and you can exhibit lots of different behaviors depending on the values of the two parameters. It's very hard to find a point on this space if I'm always optimizing to be 0.1% better than the next guy, because I have 10 other parameters. I have a half dozen parameters that are correlated with load, and a half dozen parameters are correlated with temperature and so on. So you have to really think about just one. But I think the quality of the data is going to be a load parameter, and then there'd be various ways to try and control that.
I'm wondering if I want to design a monitor for early development based on your distribution, and say that I can focus on the empty part for maybe training accuracy and the tail part for statistical possible potential generalization accuracy.
All right, so I said I don't like to train because it's hard to train it, but really we've done training. How do you use this for training? I don't know, because it's a fairly coarse measure, and a lot of times models building convolutions or something which capture local correlations that may be hidden from this. As a hello world, and I don't think it's a final version, but as a hello world, if you want to be state of the art take the inception, train a bit more. You should do better because we have a metric. The fact that there's a dip there means it's not, there's a bottleneck in the layer. Maybe the bottleneck, you compensated for with other stuff, but at least when you pull out this layer, there's a bottleneck, and so you should be able to smooth that out and get better correlations over multiple sizes. So as a hello world, if you want something state of the art, optimize this stuff to be as heavy-tailed as you can. Drive the training error to zero and keep training, pound on the loss, and that should change the alpha parameter to be slightly less. Now this is one of these things, once you use that, I forget the economic rule, once you use that as a validation measure, the counterparty will say, well, I can put this into the data and devalue the quality metric. So I don't know that it's robust in that. It's a may not be, that's another question. I think from the scientific perspective, you could do that. You could also say, listen, what we've highlighted is that you can have, you're either a perturbative or a non-perturbative approximation of some random Basel level. And if you're a perturbative approximation, pull it out, use a look for bulk plus spike, and pull these spikes out. And don't degrade the quality of the bulk, because I want a clean separation between scales. You might say, I'm modeling fluid flow over many size scales. in which case you want a couple of size scales together. So you should encourage stuff to pull out of the bulk. And how do you do that? You have several different control parameters, and you tweak those to use out. Now, it might do marginally worse on prediction quality, but you use this as a design principle to engineering correlations over multiple size scales. So yeah, so I think you use it in those ways.
Can I follow up on that then? If you were to do something like you want to do with control, would you want to engineer this to pull out these output, and you say like these are the things that might actually go try to control the system? Is that
So there's a couple, I don't know. There's a control, but by control parameter, I meant, you go to the wall and you flip something, and that's a switch that controls something. But of course, it's a very indirect control of the actual temperature in the room. So there's a question about what do you want to do with these spikes? That's something in the model. The other question is how do you control that? I'm guessing once they're pulled out, they're probably relatively easy to control, just because you've separated them from other stuff, and you could probably fiddle with them if you wanted to pull. I mean, I could imagine, you saw boom, 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 boom. I mean, I can imagine you could coalesce them into one scale, and you could sculpt those and do different things like that. That could be an interesting thing. Well, they should be similar sizes for physical reasons. You could say, it's probably going to be a little bit harder to control if you really want the heavy-tailed case, because there you're going to have something over many size scales, and so how the control parameters that you have, whatever, how do you make the power law parameter a little bit less? I don't have a good answer besides count on it and make sure you have it sort of saturated, which is sort of what people like doing anyway.
I'm very out of my own here, but this sounds like Bayesian or something, and you got these 5 + 1 are sort of your priors or something. Is that?
Yeah, so Bayesian is the sort of thing that either I have an informed opinion about or I don't. If I do, I'm going to make half of you, or at least the half of you that know what Bayesian versus not is, upset. So I don't know how I can answer that, but I don't want to interpret this in terms of Bayesians or frequency just yet. I think you could. I do think minimally, operationally, what a physicist would do is come down on one side of the Bayesian frequency divide and then say, I don't know what you're talking about. I don't know what that is. I just do stuff. I measure numbers. And so this is adopting that same sort of methodological approach. And so in some sense, yeah, I mean, what we're saying is that there's a limit state. I don't know the universe or not Bayesian. And these are possible things you could train to. Maybe there's a finer taxonomy. But each of those should have sort of an implicit prior or something. I mean, so either, the random might be like an naive Bayes and make a minimalist assumption. I mean, the bulk plus spike is a perturbative approximation of that, the spike covariance model. So there you're signal plus noise. What I don't know is what's the way to model the heavy tails. So there's a range of mechanisms to generate heavy tails with self-organized, from physics, from self-organized physicality. I mean, there's fewer in sort of statistics and machine learning land, but fair question. I mean, what would be a natural prior? I mean, you could have a Gaussian prior with a Gaussian overvariance. People have done things like that. I don't know if that makes sense or not.
Last question? Did you have one? Or,
I
yeah,
was
one.
just looking at the static analogy for overtraining and memorization.
Yeah.
Explanation or something.
Overtrain. So memorization is one of these words, and it meant something very particular years ago. And now people use it in sort of a pejorative way. Oh, you just memorized the day. And you ask them, what did you mean memorize? And they basically say, I drove the training error to 0, which you can define to being memorization, and you can define it to be anything. You're using the word memorization. So if you go to the ML meeting next week and condition on people that are talking about memorizing, that's what they'll mean. You just drive the training error to 0. That's very different than memorization, from, I guess I don't have the reference yet, 30 years ago. There, you had a phase where you got perfect. And perfect could mean good, but very good. Quality prediction. You had a phase you got poor, and you got a spin glass phase. And so, in the spin glass phase is more like where you memorize, where I could give you a single pixel of one image and you could find the class. And so it's not driving the training error to 0. It's more like you're in this phase, you exhibit this pathological non-convexity, and anything in that basin would drive you to the minimum. So people are talking about memorization these days, and even in that paper that we cited about why it works, or whatever the title was, rethinking old ideas. I mean, the way they use memorization was a little bit different than the way that had been used in the past. So I think there's an interesting question about driving the training error to 0 and viewing the parameters essentially as a resource to exploit. But you don't need to talk about the old school memorization for that.
I would just say the generalization is, that memorization is no longer generalizing.
Yeah, so that just means you're in some phase where you get a training test split. Yeah. So I think the question that there is something that is in statistical mechanics, but less so in ML, is do you have sort of a representative sample, which breaks down in that sort of extreme phase. But if you have a representative example, you choose something today, you choose something tomorrow, they're roughly the same, which is why you do the usual denoising thing. If you have a non-self-averaging, a non-representative example, then that's just out the door. And you don't see that in the limit that you typically go on machine learning. Fixed model size, let number of data points diverge, or vice versa. You only see that in this thermodynamic limit.
Okay, so let's hit coffee. Bathrooms are straight back there. There'll probably be a run on that, and then we still have coffee out here. We'll come back at 10:30. Thank you, Michael.
All right, thank you.